So video 2 of section 12.8, change of variables and multiple integrals. This will be the practical set of material. We'll do 3 examples. So we're starting with, we're given a change of variables in this problem. It says use the change of variables. These should be familiar. We looked at this transformation in the previous video in an example earlier in these notes. And we found that, well, this transformation converted a square 0, 1 by 0, 1 to a more funky looking curve. Two half parabolas intersecting each other with some line segments below. And what we realize when we look at this function and this function, if we solve for x in each of these and we're restricting y to be greater than or equal to 0, we have these two curves here. If we're restricting y to be greater than 0, that's exactly the region that we saw previously. So we know that we can go back and look at the drawing from the previous example, but what I'll note is this. We had something that looked like, this region looked something like this. Right? Without that y greater than or equal to 0 restriction, we'd have the bottom portions of these curves too. But we've only dealt with, we had already taken care of transformation for this region from a square 0, 1, 0, 1. Now, of course, the motivation for converting this, or for finding a transformation of a region like this one back to a square, well, it's just to simplify our limits of integration, simplify the region that we're integrating over. So much of the hard work is done here, because if we were looking at a region like this, to come up with this transformation just takes practice, experience, some insight. It's hard work to do that. Most of the problems we'll see will be given transformations and asked to use those to then evaluate an integral. So that's nice. There are a couple where we'll have some simple regions that will transform and use change of variables for. But this will be harder than anything that we do. Luckily, we're given that that transformation. So we note that our transformation t of u v is given as our x and y functions of u and v. It's a transformation from 0, 1 cross 0, 1 to this space, as we've already pointed out. So it changes an integral that would go from x limits of integration left and right, top or bottom and top, and then y goes from 0 to 2 to an integral over this rectangular region, which is nice. We prefer rectangular integrals because they're just easier to deal with typically, as long as the integrand is manageable. So we're using our integral formula from the previous page right away. Y is a function of u and v. This is the area in our image region R, which is 0, 1, 0, 1. Or sorry, which is 0, 1, 0, 1. So now y is a function of uv. Y is 2uv, and then times the Jacobian of this transformation. Well, we've calculated the Jacobian off to the left, and we end up with 4u squared plus 4v squared after we take this 2 by 2 determinant, slash left to bottom right, and that's positive, minus slash top right to bottom left, and that comes out positive as well thanks to the minus sign. So plug that function in, and we've got the following: the factors of 4 multiplied by 2 to get an 8 as a constant out front. We have u cubed v plus uv cubed, and this follows pretty standardly as a double integral at this point. Evaluate or integrate with respect to u first. Power rule on both functions of u leaves us with this and this. Apply the limits of integration from 0 to 1. That's nice and clean. 0 just contributes factors of 0. So we add 0 to it, nothing really changes. And we have the following as an integral in v. Power rule with respect to v leaves us with this expression, and we come out to ultimately 2. So again, the hardest work here would have been to come up with this transformation, and also to then realize what this transformation maps from one space to another. We won't always be given all of that. Typically a full problem will be, we're given a transformation to use, and we're given functions like this, and then we're asked to find the integral over the region R, for those given functions. So we've already done the first work and another example of figuring out what we map to from UV space, in other words, finding that rectangle. So this problem, it was a little bit shorter in that regard. Now, this is nearly as complicated as it will get in any of the exercises we see, so don't panic there. We'll have some fairly simple transformations and regions in our exercises. Okay, so let's work a little bit more with just the transformations themselves. So we're asked to find a transformation T from S in the UV plane onto the region R, which is the parallelogram in the XY plane with vertices, so on. Okay, so we draw this from left to right. We're trying to get from some simple region in the UV plane to the more complicated region that we've been given in an XY plane. So the first thing we know is this parallelogram. So we can plot that in the XY plane. It's good to have a sketch handy so we can think about how we might want to transform this. The more similar object we transform this object on the left back into in our UV space, the easier our transformation might be to come up with. So I think it makes sense to try to transform this parallelogram into a rectangle with a point at the origin, with one vertex at the origin. So then we can, or even in this case, we choose a square. This is completely arbitrary. All right, we choose S to be the square 0, 1 by 0, 1, because that's literally an arbitrary choice. We've just decided we want to map that parallelogram back to this easy square right here. Okay, and now it's our task to figure out how to do that. So we'll identify edges. What we'd like to do is we'd like the edges to match up as we see here with the different indications for each one of them. So they'll all match together. And that'll kind of divide the work up for us. So we'll know which line segment needs to map to which line segment. We would prefer and hope to find a linear transformation for each of x and y. We want x and y to be linear functions of u and v. So in other words, no squares, no u times v, nothing like that, no cosine or exponential functions. So we want it to look something like this. That's what we hope to be able to get. Now, it may or may not be possible. If we're transforming from some polygonal region like this, or even a trapezoid or a triangle, something like that, it's still possible to, it will always be possible to have a linear transformation take us back to this rectangle. So that's one thing we can count on, and any of the problems we'll do will be polygonal regions, so we can pretty much always bank on being able to write our functions down like this. Now let's have a look at what we've done here. We said that x is a function of uv, some unknown coefficient a times u plus an unknown coefficient b times v plus some unknown constant value c. Y we've done very similarly. We have unknown coefficients m, n, and k. We need to determine all 6 of those constants. All right, now what we'll use is the fact that we want to map this line segment to this line segment, and so on for the other 3 through these functions, x and y that we have here. Okay, so just as we did to determine what a transformation did once we had one, we'll use that process in reverse. So we'll look at, it looks like we're going from 0, 0 to 0, 1. We'll look at how each point is mapped. And we might not even worry about each line segment. We'll just look at how each point maps to each one. So we know that we want 0, 0 to coincide with 0, 1. The way that we've made these identifications at the bottom left for each of these polygons is such that those 2 points should now line up. So we need our functions x and y, functions of u and v, to map 0, 0 to 0, 1. Okay, so that gives us these sets of equations in our unknowns. So x of 0, 0 needs to be equal to 0. Plugging in 0, 0 to that needs to be equal to our x coordinate of 0. So if that's the case, u and v are 0. So that leaves just c in our equation for x. So c needs to be equal to 0. So we know our constant c for our x function. So we've determined one of our parameters here. Now y, at 0, 0. Plugging in 0, 0 to our function of y, we need to get the output of 1 for our y coordinate. So this needs to be 1. So in other words, when u and v is 0, that equation needs to be 1. So when u and v are 0, m and n disappear, and that leaves k as needing to be equal to 1. So we've determined c and k in just one point, one vertex here. So we update our equations for x and y. The unknowns that we need to determine are now a, b, m, and n. We keep updating information as we determine constants and moving along in the process. Now from 0, 1 to 0, 3, let's confirm in the graph, that's what we're hoping for. 0, 1 to 0, 3, yes, the single arrow and the double arrows are matching up here. That vertex should be 0, 1 on the square and 0, 3 in the parallelogram. So these 2 points need to map to each other. And we'll do that work down below. So plugging in the point 0, 1 for uv into each of x and y's arguments, in other words, into each of these functions, with the constants that we already know, well, u is 0, so that just leaves bv plus, well, c is 0, that just leaves bv, or b times 1 in this case. And similarly for y, u is 0, so it's nv plus 1, or n times 1 plus 1, being the constant k. Solve for b, solve for n, and we get that b is 0 and n is 2. We update our equations for x and y. B is 0, so we only have the term x equals au for that function, and y is mu plus 2v plus 1. All that's left to determine is a and m for each of these equations. And we look at the very last one, the next coordinate pair. 1, 1 needs to map to 2, 2. Is that how we have this drawn? 1, 1 is that vertex, 2, 2 is that one. And this is the vertex between those segments. Yeah, that's exactly what we'd like to happen. Okay, and we have x, 1, 1 needs to be equal to 2. So when we plug in the uv coordinate 1, 1, we need to get an x coordinate of 2. When we plug in the x coordinate, or the uv coordinates 1, 1 for y, we need a y coordinate of 2. So that determines the equations we see below. When uv is 1, 1, we have, well, x of au needs to be 2. So there's a times our u coordinate of 1 needs to be 2. Similarly, our y equation is a little more complicated. U is 1, so it's m times 1 plus 2 times 1, v is now 1 in this case, plus 1 equals our required 2. Solve for a, solve for m. We get a is 2 and m is negative 1. Update our equations for x and y, and we end up at a fully developed transformation. 2u is our x coordinate, and y is equal to negative u plus 2v plus 1. So our transformation overall as a coordinate pair is this. And we can find the Jacobian of that and proceed with whatever integral we might have been interested in. So it's not, it's a work-intensive process. It's not impossible. You just have to organize your information and work, pretty much any problem similar to what we've done here. I recommend working with vertices and identifying which vertex needs to map to which vertex. Most of the problems we do should work out just fine like that. Again, we'll only be dealing with, in nearly every exercise that we do, a transformation or come up with a transformation for polygonal regions to rectangles. So it shouldn't be too difficult. We'll note that we never actually used the mapping from 1, 0 to 2, 0. That's kind of nice. What you can do is confirm that the transformation we come up with actually satisfies that. So you want to check that t of 1, 0 actually maps to 2, 0. And that would give us some confidence that the transformation we built is actually doing what we'd hoped it would. So I'll leave that to the reader or the viewer to do. So let's move on to our final example, and this is a short one. We can develop the same theory we did before for triple integrals, and we'll only have 1 or 2 exercises like this, but the Jacobian for a for such a C1 transformation from R3 to R3, or subsets of R3 to subset of R3. We'll have x equals a function g of u, v, and w, similar for y and z. Our 3x3 Jacobian matrix determinant is the following. It's a 3x3 determinant, and it's denoted similar to the 2x2 Jacobian we saw before, only with an extra dependent variable z and an extra independent variable w, which creates an extra partial derivative for each of x and y, and for this new function z, adding a column, and then it creates a new row for this new function z, who has a partial in all three of those variables. So this is a square matrix. We'll see that for any coordinate transformation, that will always have a square matrix result from that, but we'll really only deal with 2x2 and 3x3. So just to see this Jacobian formula at work, we're given a transformation for x, y, and z in terms of u, v, and w. We're asked to find the Jacobian of it. So here's the notation for that. And we take the partial of x with respect to u and get 0, with respect to v and get 1, with respect to w and get 2w. Now we do the same for y. Take the partial of the function y with respect to u, then with respect to v, then with respect to w. And do the same for the function z along the third row. Partials with respect to u, v, and w as we move along left to right. Find the determinant of that matrix. Again, we can use the diagonals method if we like for a 3x3, or I've used cofactor expansion along the top row. This is where I'll take each element of this row and multiply it by its submatrix. So if I'm going to do the 0 element, the 0 position, I omit this column and I omit this row, and I multiply that 0, I'm crosshaired on, and I find the determinant of this 2x2 matrix written right here. Now, parity tells me that this position is negative, but I'll have a 1. So negative 1 times cross through this. Our submatrix is made up of this column and this column, and I'll find that 2x2 determinant. And I'll do the same thing. Parity tells me that this is a positive position. So parity is basically this. You move left to right or up and down in a matrix, positive, negative, positive. You just change the signs of things as a checkerboard, essentially. And if we move left to right, we go positive, negative, positive. Top to bottom, we go positive, negative, positive. If we started in the second row or second column, we'd go negative, positive, negative. Just to point that out. But our last element here is 2w, is at the position of 2w. And we'll do, this is our submatrix. Whatever is not crossed out, we have this here, times 2w. And remember, 2x2 determinants are straightforward. We've done a couple already in these notes. It's this product of this minus product of this, and we carry that out for all three. Ultimately, we end up at 1 plus 8 UVW. So it's nice to see this, this cofactor expansion method. Parity was this thing here. But again, it's a 3x3 matrix. You could do what we've always done for these, and we've always taught is 2U and 1. It's just nice to have another method in our back pocket in case we want it. So either way, these are pretty straightforward calculations. There are a lot of them in this section, and really this section can be thought of as being a lot about the Jacobian than anything else, because often those transformations will be worked out ahead of time for us. Okay, so that's it for 12.8. It takes a lot of practice to learn these transformations, but then, like I said, the Jacobian should be pretty straightforward.